Good morning, dear students. Welcome to our session of microwave and antenna. So in the previous sessions, we discussed regarding Smith chart and what are the different types of Smith charts we can come across. That is Smith chart utilized as a Z chart. That is what we had seen. So this one, and the Smith chart used as a ZY chart. And this same chart can be utilized for as an impedance chart also. With continuation with those, we discussed even regarding a few of the problems in which we tried to identify. Say, first we tried to plot a given impedance on the Smith chart. Then we tried to look out what is the constant VSWR circle, how we plot that. Then apart from that, using that constant resistance circle, how we identify the reflection coefficient, its magnitude, and its the angle, that is reflection coefficient angle. Then apart from that, even we saw other problems wherein we try to estimate at a given distance what is the distance associated with they say for example we solved regarding identifying a distance at which we have a voltage minima or a maxima from the load. So in one of the problems we had those discussions, that is if a circuit is short circuit and Vmin is given at some position, then identify the other parameters. Like as input impedance is given, how I can identify the load impedance, provided I know what is the distance between the input and the output, that is the generator end and the load end. If I know those parameters, I'll be able to estimate the unknown parameter. So these were a few problems what we had discussed in the previous sessions. Then in continuation with those aspects, right? So this problem was the last problem what we had discussed, in which we had to identify the unknown impedance at the load end. So that we have solved this problem, and we saw what are the values which is associated with the unknown impedance. So in continuation with the last few problems. So I'll just discuss a few of the problems and then wind up for this entire session. So here, next problem, what we can observe is a Vmin occurs at 18 centimeter from the termination. That is, termination implies from the load end. That is, we have a voltage minima at a distance of 18 centimeters from the termination, that is the load end, of a lossless line of length 52 centimeter. So the length of the transmission line is specified to be 52 centimeter. Adjacent Vmin occurs at 20 centimeter apart. So there is one catch what you have to look out over here. That is, when I consider two voltage minima, successive voltage minimas, that is what this adjacent Vmins imply. They are separated by a distance of 20 centimeter. VSWR is 2.5 and Z0, that is a characteristic impedance, is 300 ohm. Using the Smith chart, identified the input impedance and the load impedance. So in this case, you can observe that the unknown parameters are input and the load impedance. But he has specified that you have a voltage minima at 18 centimeters from the load end, and 52 centimeters is the load transmission line length, and 20 centimeter is the distance between two voltage minimas that are successive with each other, that is adjacent to each other. So these are the parameters what we have. Using this, we need to identify the input impedance and the load impedance. So in order to look at this aspect, so in this, these are the parameters what they have given. So we need to identify the normalized parameters. Now, if you just observe in this problem, right, Z0 is given. So any normalization and denormalization with respect to impedances can be done. But what about the distance parameters? I need to divide this distance by wavelength. wavelength at which the entire transmission line is operating. So now here, if you just observe, there is no direct specification of wavelength. But when we observe the voltage minima concepts, right? Say if it is. So if we observe over here, what happens is whenever we consider minima or maxima. So here, this is a Vmin, voltage minima, and this is also a voltage minima. So it can still continue, and I can have another voltage minima at this point. Okay, I can have Vmin at this point. Now, what is the catch we have to look out is, now in this case, what has happened is they haven't specified the wavelength, but it is specified in an indirect way. So whenever we measure the distance between two successive minimas, so whether we measure the distance between this minima and this minima, that is the successive minimas, it will be always equal to lambda by 2. Now suppose there was another Vmin over here. So this was like this, and there was another Vmin over here. And if I measure the minima distance over here, it would also be equal to lambda by 2. Now the same case holds even for maxima. So at present we are interested in minima points, so we can discuss those points. So but just for specification, if this is a Vmax point, that is the voltage maxima. So we have two successive voltage maximas. Distance between two successive voltage maximas is also given by lambda by 2. So this is the thing what we have to look out when we are dealing with, when we have to identify the wavelength at which the entire circuit or the microwave circuit is operating. So now in the problem what they have specified that adjacent Vmins, that is voltage minima, occur at 20 centimeter apart. So what does this imply? So if I look at this, so I have a voltage minima over here and a next successive voltage minima over here. Now, if I measure this distance, it is around 20 centimeter, which is actually equal to lambda by 2. So therefore, what is the value of lambda? Lambda is 40 centimeter. So lambda, that is the wavelength, is given in an indirect form. So using the distance between two successive minimas, which is 20 centimeter, I obtain a wavelength which is equal to 40 centimeter. Now I can normalize all these values and then utilize those values in the Smith chart. So now we know what is VSWR. He has given 2.5, so which will be utilized to draw the VSWR on the Smith chart. So now, what is the specification he's telling? He's telling that 18 centimeter from the load, I have a minima. So Vmin is present at 18 centimeter. So this implies even there is a Zmin at that point. There is a Zmin at that point. So now, no need to worry about this. So adjacent minima is 20 centimeter, so that is which is equal to lambda by 2. So therefore, when I estimate that, I get lambda is equal to 40 centimeter. So now I know length of the overall length is 52 centimeters and rho is given by, which is VSWR is 2.5. Now I need to identify Zin and the load impedance ZL. So these are the aspects what we have to look out for when we are looking into these things. So this Z what is specified, right? It is actually associated with the direction, that is the Z axis. So it is like you have placed it along the Z axis and you are measuring the value of Z. So that is what they are specifying in the problem. So now let us look at the other aspects. So first I need to normalize the values. So the 18 centimeter which is given, so which is the Vmin point from the termination. From load end, if you move a distance of 18 centimeter, you encounter a Vmin. So that is what they are specifying. you encounter a Vmin. So now we normalize this 18 centimeter by dividing it by the wavelength, so which is around 0.45. So first step is to normalize the values. So here Zmin, that is the Vmin location which is there, which is at 18 centimeters, that we have normalized. Now we need to draw the VSWR circle, which is corresponding to rho equal to 2.5. So what we have to do is we have to refer to the voltage standing wave ratio VSWR scale. On this, keeping this as the center, I need to mark where is 2.5. Where is 2.5? So here, if I just see where is 2.5, 2.4, 2.2, 2.3, 2.5. So here we can see that approximately somewhere here is 2.5. So whatever value we are getting this, so I need to measure this distance parameter. I need to see how much is this in terms of say centimeters, and using that as the radius of the circle, VSWR circle. Using that as radius, we plot the VSWR circle. So whatever radius I get, I consider that. So it is like OA, and I draw the VSWR circle on the Smith chart. So here we have, so here you can just observe. So this distance is measured. So from the VSWR scale, and that is considered as the radius of the VSWR circle, taking center as the center of the Smith chart and radius equal to the rho equal to 2.5 corresponding value, you draw the VSWR circle. So this is the VSWR circle. Now this VSWR circle will help us to identify the load point and the input point. So now what we have done, we have utilized these aspects. That is, we plotted, we have drawn the VSWR circle. Now, what is the specification? He specifies that from the termination, that is from the load end at a distance of 18 centimeter, you obtain a Vmin point. You obtain a Vmin point. So using this, we need to identify the aspects which are present over there. So here what is done is, so we can observe that Vmin is given by this point and Vmax is given by this point on the VSWR circle. Now what is the specification? This Vmin is at a distance of 18 centimeters from the load, is at a distance of 18 centimeters from the load. So if I just consider this one, right? So this is load, and this side I'll be having the generator. So at a distance of 18 centimeters, say at this point, at 18 centimeter, I have a Vmin. So I know that this point C corresponds to Vmin. But in order to identify the load point, right, what I should do is I should move towards the load by a distance which is equal to 18 centimeter. I have to move a distance of 18 centimeter. So 18 centimeter corresponds to how much normalized value? 18, it corresponds to 0.45. It corresponds to 0.45. So what I have to do is, if you just observe on the Smith chart, right? If I have to move towards the load, what is the direction I should follow? If you just observe wavelength towards the load, I should be moving in this direction. That is in the anti-clockwise direction. So referring to that point, Vmin is located at this point. So from this point, you need to move a distance of 0.45 towards the load. So that is on this outer scale, what you have, you start off with this reference point and you traverse a distance which is equal to 0.45. So that is Here you can observe. So this dotted arrows what they have shown, it is equivalent to traversing a distance of 0.45. So on Smith chart, how do I mark this? So if you just start from this point, right? Since Vmin is given, so Vmin we have at this point. So I keep on traversing. So if you just have a look at the scale below, so this is 0.05, 0.06, 0.0607, so on it continues. So up to this point, I have 0.25, 0.26. So where is 0.45? So if you keep on continuing, I have 0.38, 0.39, zero point 0.4, so on. I'll be having 0.45 over here. So what I do is, I have drawn the VSWR circle. And from this point, I traverse a distance of 0.45, which is over here. So now what we do is, draw, we inter, we join these 2 points. That is this point which is there. We join this point with the center of the Smith chart or the center of the VSWR circle. So first we identified this point, that is A dash. Now what we do is we join A dash and O, where O is the center of this VSWR circle or the center of the Smith chart. So now when we join these two lines, what happens is this VSWR circle is cut at point A. That is, the straight line OA dash and the VSWR circle intersect at point A. So this point is nothing but the load point. And this point, when I read it, it gives me the normalized load value. It will give me the normalized load value. So if I read this, if you just observe, the upper part is inductive. The upper part is inductive and it is positive since it is a Z chart. Since it is a Z chart. So load, if you just observe, load is having a resistive component and inductive component. Now what you have to do is you have to read the impedance value which is associated at point A. So when we read that value, it corresponds to 0.435 plus. Why plus? It is in the upper half part of the Smith chart. And since it is a Z chart, it is an impedance value. Sorry, it is a inductance value and it is positive. So therefore it is plus J 0.27. So this is the normalized value what you are getting from the Smith chart. To denormalize it, what you have to do is you have to multiply this with Z naught. So this is what is specified over here. So this is the load impedance what we have obtained, which is 130.5 plus J81. So this is the load value. Now I got to know what is the load, this thing, and where it is located on the Smith chart. Now I want to know what is the input impedance. So what he has specified? He has specified that the length, that is the length of the transmission line is 52 centimeters. So indirectly what is mentioned, if you just consider it, ZL, and there is a generator over here. So here I'll be having the input impedance. This is the load impedance. So now I got to see what is this on the Smith chart. Now, if I have to identify the input impedance, right, I have to traverse a distance towards the generator by 52 centimeter, by 52 centimeter. So now if you're using the Smith chart, we have to first normalize this 52 centimeter. So when I normalize this 52 centimeter, how much I'll get? I'll be getting a value of 1.3. That is the length what is given, right? Length divided by wavelength is giving you 1.3. Now, how do I represent 1.3 distance on the Smith chart? So now we have identified the load point. So from this load point, right, you have to traverse a distance which is equal to 1.3. Now remember, say we'll just consider one simple case. So if I start from 0 over here, say for example, I'll take this chart. So if I start from 0 over here, if you just see, if I complete one entire rotation, say either if you're moving towards the generator or moving towards the load. So if you just consider any one. So if you just consider that, if you just observe what is happening is, so 0.0 is here, 0.04, 0.05. So on it continues, zero point 0.1, so on it continues. And here what we are having, we are having 0.25. We are having 0.25. And still we continue, right? When we continue and when we complete one entire rotation, so it is 0.49, this value will be zero point 0.5. This value will be zero point 0.5. So one entire rotation, it will be zero point 0.5. Now another zero point 0.5, if I add, what happens is I'll be traversing completely and again coming back to this position. So if I traverse two times, it will be zero point 0.5 plus zero point 0.5. It will be zero point 0.5 plus zero point 0.5, which is how much? It is equal to 1.0. It will be equal to 1.0. Now the same thing holds even if you're traversing in the anti-clockwise direction. So if you start from this point and with one rotation over here, it will be 1.5. Sorry, a 0.5. Again, if again you start off and you continue, so it will be like 0.5 plus 0.51 plus 0.52, 53, 54, so on it continues. So here will be again 0.57, so on it continues. It will be 0.5 plus 0.5, which is equal to 1.0. So one entire one entire rotation gives you zero point 0.5. That is actually it is equal to lambda by 2. It is equal to lambda by 2. So zero point 0.5. So again, if you traverse, it is another 0.5, which is 1.0. Now, in our case, what is happening? Additional 0.3 has to be traversed. So additional 0.3 means again from this one, from this location, what we have got, we have to traverse a distance of 0.3. So that will give you the reading associated with 1.3. In which direction I have to move? I'll just check. We have to check it out from the problem. So in problem, what is specified? It specifies that now we have obtained the load impedance. So from load, we have to move a distance of 52 centimeters. So it is that you should move in a direction towards the generator by a distance of 52 centimeters, which is actually equal to 1.3 in the normalized form. That is 52 divided by 40 centimeters gives you 1.3. So from this point A, if I traverse one entire, if I complete one entire rotation and come back to the same point, it is equivalent to traversing a distance of 0.5 on the transmission line. It is equivalent to traversing a distance of 0.5 centimeters. So another 0.5 centimeters, I need to, another 0.5 I have to rotate. So again, I'll start from point A and just complete back. So when I complete back, I have 0.5 added. So it is 1.0. It is 1.0. So now what I have to do is, how much is remaining? I had to traverse 1.3. So already I have traversed 1.0, 0.3 is remaining. So from this point, right, you traverse a distance of 0.3. You traverse a distance of 0.3. So if you traverse that distance, you will be able to locate the input point. So you start from this point and traverse a distance equal to 0.3. That is the remaining. So why only this much is shown is you are traversing it two times, 0.5 plus 0.5, which is 1, and plus 0.3. So you have to move towards the generator. If you're moving towards the generator, you have to traverse in this direction, that is clockwise direction. So from this point, you traverse it in the clockwise direction. Two times when you traverse, you reach the same point, which is 1.3, and then you traverse the remaining distance, which is 0.3. So, so what we get is on the outermost circle, which is corresponding to the wavelength towards the generator, you mark that point, that is, which is 1.3. So which is B dash in this case. So now what you do is you join B dash and O. So when you join these 2 points, right, this line intersects the VSWR circle at point B. So this point B is nothing but the input point. That is the point which gives you the normalized input resistance value. So now read the impedance value over here and you'll be getting the normalized value associated with the input impedance. And multiply that value with Z0, you will get the overall input impedance. Now, if you just see, the input impedance value, that is point B, is located in lower half, and this is the Z chart what we are using. So this one gives you the capacitive value. This one gives you the capacitive value. So therefore, in the imaginary part, that is the reactance part, you will be having a negative. So based on this, you can see what we have over here. So based on the chart, we get zero point 0.9 minus, indicating that it is capacitive, minus J 0.88. Now multiply this one with the Z naught, you will get 270 minus J 264 ohms. So which is the input impedance. So these are few problems associated with these all aspects. Now we'll look into other aspects of Smith chart. So here, one thing before going into the discussion of single stub matching, right? We need to see how we can use the Smith chart as an admittance chart. How we can utilize or how we can plot the admittance onto the Smith chart. So for that, what we'll do is we'll directly refer to a problem. So one simple thing what you have to note down is so whenever we have any impedance value, if I want to know what is its admittance, you just take 1 by Z. You just take 1 by Z. And if you just remember in admittance we have in sorry impedance we have it is like plus minus jx. So it is like this. So when we take inverse of this, we get conductance minus plus. When we take inverse of this, it is like 1 divided by r plus minus jx. So when we take that and we represent it in terms of admittance, right, we'll be having conductance minus plus j times the susceptance value. The susceptance value. So here susceptance, so since we are utilizing the graph itself, that is the same graph. So in this case, I'll be using the same graph itself for plotting the inductances, plotting the admittances. Then what happens is if you're using that, so refer to this part. Capacitive susceptance is given over here, and since in conduct in admittance, right, capacitive is positive and inductive is negative. Inductive is negative. If this you are using for the plotting of admittances, so positive values will be plotted over here, but remember that it is capacitive, and negative values will be plotted here, but it will be inductive. So that is what this chart specifies. So here also you can observe that if you are using this one for the susceptance, if you're using this one for the susceptance, so here you can refer, it should be minus JB. It should be minus JB. So if you're using this part for susceptance, then it should be plus JB. That is if you have Y is equal to G plus JB. So that point will be lying here. And if you're plotting Y is equal to G minus JB, that point will be lying in this part. So that is what you have to take care. But if you're using the other chart, right, ZY chart, you should be a little bit careful because what happens is the inductive reactance or the capacitive this thing is given over here. This what they're specifying is actually associated with the Z chart. So you should be just careful when you're utilizing this. Okay. So at present, we'll discuss, we'll stick to one chart and then we'll go ahead with the discussion. So here, when we want to plot that, right, when we want to plot any admittance on the chart, I know what is Z. I want to plot its admittance value. I want to plot or identify its admittance value. What I can do is, you can refer to these things. So using Smith chart, convert the following normalized impedances into normalized admittances. So we have this as normalized Z value, which is zero point 0.3 plus J 0.4. Now, say I'll just consider this point and I want to see what is its, say, normalized admittance. Now, if it is inductive in this case, right, if this is plus, it should be minus in the admittance case because Inductive is negative in that case. So here what is done is, first you need to plot this value. First you need to identify where is zero point 0.3 plus j 0.4. So that is what they have shown over here. So it is point A. So that value is lying somewhere here. So after this, what we need to do is we need to locate a point which is opposite to this point. We need to identify a location of point which is opposite to this. So in order to do that, what we have to do is we have to draw a VSWR circle. We have to draw a VSWR circle. So we'll not be touching these things. It will be same this thing. I am just referring to point A, which is actually associated with zero point 0.3 plus J 0.4. So point A is associated with zero point 0.3 plus J 0.4. So now what I do is I consider the center as O and the radius equal to OA and draw a VSWR circle circle. Once I do that, what I do is I extend the line OA. I join the points A and O and extend it to intersect the VSWR circle. So this point B what we have is nothing but the admittance value which is associated with the point A. So that is what we have to look out for. So in order to identify the admittances, so first we need to plot the impedance value on the Smith chart, and that is the normalized impedance value on the Smith chart, and draw the VSWR circle which is associated with that impedance. And we need to identify the point which is lying opposite to point A, what we are showing over here. So in order to mark that point, right, what we do is we join point A and O and extend it so that it intersects the VSWR circle. So this point of intersection gives me the admittance value. Now we need to read this point B value. So in our case, what we have is when we read it, we get it as 1.2 minus J 1.6. So similarly, if you have any other values, right? Say if I want to plot 1.2 minus J 1.6, so you can continue with the same aspects and then identify those values. Okay. So just a few more points to note down before going into the problems associated with the single stub matching. So here we can observe that this is just a part of the Smith chart what they have specified. So if you just observe, we have in this case we'll be having the conductance circles. So there in the Z chart, what we had the resistance circle. But if I want to utilize the same, what I do is I refer to those circles as the conductance circles. And in Z, I have the reactance circles. But in Y, what I'll be having, that is the admittance, I'll be having the susceptance circles. I'll be having the susceptance circles. So now what happens is this part will be still positive, this part will be still negative, but since it is used as a Y chart, so this is entirely Y chart. So what happens is the upper part will give you the capacitive susceptance and the lower part will give you the inductive susceptance. Whereas in the Z chart, it is the opposite. This will be inductive reactance and this will be capacitive reactance. The sign remains same if you're using the same chart over there. So now what happens is a few more things to note down over here is you will be having circles which are called as the conductance circles. And one important circle what we have to look out is this circle. That is this G is equal to 1 circle because it is required for us when we are dealing with stubs. Then apart from that, this the outermost circle what we have on the Smith chart, that is this part. This is corresponding to G is equal to 0 circle. G is equal to 0 circle. So apart from this, a few more points to note down. We have an open circuit at this end, and we have a short circuit which is identified by point B. Point A gives you the open circuit analysis, and point B gives you the short circuit point. So at this case, what will be there? G will be equal to infinity. G will be equal to infinity. But what will be R equal to? R will be equal to 0. R will be equal to 0. And here, what will be the case? It will be equal to G is equal to 0 will be the case over here, and R will be tending towards infinity. So at this point. So this is what we have. Then apart from that, if we are moving towards the generator, you have to move in the clockwise direction. And if you're moving towards the load, you should move in the anti-clockwise directions. Now here you have the voltage maxima points, but in Z chart what you had voltage minima points at this end. That is, so here you can just observe we have a Vmin at this point. But when we go for using this chart as the Y chart, right? Using this chart as the Y chart, we should be careful with these things. So here we'll be having the Vmax for when we're utilizing the Y chart, and this side will give you the Vmin point. So now, but in a problem, we'll be referring to Z chart itself, but these are required since we have to point, we have to locate few points using those concepts. So these are just a few things to note down in case of Smith chart being utilized as an admittance chart. So now let us move further. And apart from that, there is another one point, the reflection coefficient when you're measuring. In this case, what happens is since you consider Z and you check out with Y will be equal to 1 by Z. So this implies that Y is totally 180 degrees out of phase when we, means the angle associated is 180 degrees with respect to this. So therefore, when you have rho in Z, when we measure it using this chart, it turns out to be minus rho. This minus is nothing but e raised to j 180, e raised to minus j e raised to j 180. So that is what it corresponds. That is it is giving you the phase difference. So therefore, that is one minor change what you can look out for. So when you're measuring the reflection coefficient using this chart, you should be careful. So now let us look forward with the other aspects. Find the length of a short-circuited line which gives a normalized input impedance of minus j.5 using Smith chart as the admittance chart. So now in this case, what we have to do is we have to refer to Smith chart as an admittance chart itself. Now, here, first thing what we have to do is, first we need to locate the admittance, what is given. So in this case, the normalized input admittance is given, which is equal to 0 minus j 0.5. So here G is equal to 0 and the susceptance value is equal to minus 0.5. So this is actually the point B on the Smith chart. So that is in this figure, if you just identify, it is G is equal to 0 is which circle? It is the outermost circle. And since it is negative, right, we need to consider this part. So it implies that it is actually inductive in nature. It is inductive susceptance what we are talking of. So we need to identify that point. So that point is given over here. So since it is minus, right, we have to refer to the lower half part of the Smith chart. So now what is specified in this case? So point B will give you minus j 0.5. That is G is equal to 0 and the susceptance of minus 0.5 value we have to intersect, and that is given by point B, which gives you the input normalized input admittance. Now what we need to do is we need to join OB and extend it towards B dash. We need to extend it towards B dash. So now when we are doing that, what we are encountering is we are encountering the length parameter. So this OB line which is there, it is extended so that it intersects the lines which are present at the outermost circle of the chart. That is the wavelength towards the generator and towards the load. So these lines are intersected with respect to the line what you are joining. So O is here and B is somewhere here, and you are extending so that it intersects this scale. So for that purpose, you are moving outside and you identify the B dash value. Now, what is the next thing we have to look out? We can see over here what he has specified. You need to find the length of what? Short circuited line. So this is giving us indication what? That it is a load which is actually short circuited. Is actually short circuited. So this problem also we had solved in the other session, but there we had used the impedance. Now we are using the admittance. Now, so it is given that it is short circuit, and from the graph we know that short circuit is at what point? It is at this point. So that is short circuit as is at this point. Now what you did, you identified the input impedance. And now what you have to do is you have to move towards the load where you get the short circuit condition. So it is given that ZL is short circuited. So therefore I got to know that this is the case, but I need to move towards the load in order to identify the length of this entire short circuited line. So in order to do that, what we have to do is we have to traverse a distance. We have to traverse a distance from this point so that we reach the point A. So in this case, point A is the short circuit point. So now we measure this distance. We measure this distance. So what is this overall distance? So that is what we need to measure. When we measure, it turns around to be 0.176. It turns around 0.176. That is L by lambda is actually equal to 0.176. So therefore, length of the short circuited line is L is equal to 0.176 times lambda. So this is how you utilize. But in the impedance chart, right, you had the opposite conditions. Okay, so that care should be taken. So now let us move ahead with impedance matching. Okay, so just one problem associated with the admittance chart. So now let us move ahead. So wherein we'll be discussing regarding impedance matching, and in this case, we'll be looking forward for impedance matching using a single stub. So now why impedance matching is required? So it is like whenever you have impedance matching, first of all, maximum power transfer occurs. Maximum power transfer occurs. Then apart from that, what happens is the reflections will be zero. That is, no reflections will be involved. If maximum power is being transferred and there is an impedance match, so maximum power transfer will be happening, and because of which there will be no reflections happening. So because of this, what happens is you will not have any standing waves which are being formed in the transmission line of microwaves. So that is, there will be no reflections, no standing waves associated. There will be a maximum power transfer happening, and the loss also will be very less. So that is what you can look out when you are dealing with impedances. Now, generally, when we are looking out for these impedance matching, right, what happens is whenever you have a transmission line and we have ZL which is placed over here. Now it is not assured that this entire transmission line is matched to the characteristic impedance. It is matched to this characteristic impedance. So under that condition, I can have a maximum power transfer happening. Now, what happens is in our case, so in this case, we have single stub and double stub matching. So all these aspects are there. So in this case, what is the purpose of the stub is now here, if I try to look out for the impedance at this end, and say for example, it is having inductive component. Say let me specify it as R plus Jx. It is having some inductive components. Now I want to eliminate this inductive part. How I can eliminate this inductive part? By adding an opposite value of this inductance. By adding an opposite value of this inductance. So that is, if I have R plus Jx, just as an example, if I am able to achieve something in which case I'll be having minus Jx, then this will be tending to only R. And this one, if it is matched properly, right, then we'll be able to obtain the impedance matching. So in this case, what happens is, if say if inductance is there, you use conductive this thing to overcome this, and if conductance is there, sorry, a capacitive this thing to overcome, and if it is capacitive in nature, you use the inductive parameter so that it will be overcome. So that is the purpose of the stub. So when we are dealing with this case, right? So from the load end, at what distance the stub should be placed? That is one parameter. And what should be the length of the stub? So that is the next parameter. So these are the two cases what we have to look out when we are dealing with the single stub matching. At what distance should the stub be placed? At what distance should the stub be placed from the load end? And what should be the length of the stub what we are utilizing? So these are the two main parameters what we have to look out for when we are dealing with the single stub matching. So when we are dealing with this, we can make use of different concepts. So if you're dealing with parallel analysis, right, we go in with admittance parameters. So therefore, we have to look out for all these aspects. So that is what they have specified over here. That is input admittance at this point. If you just look at this is the parallel combination what we have over here. So now let us have a look at the problem, and then we'll try to understand the entire characteristics. So what are the steps which are involved when we are dealing with single stub matching and we are using the Smith chart? So first of all, what we should look out is, first we need to plot the normalized load impedance value. So as we have done in the previous cases, right? First is we need to identify or locate the normalized load impedance value. So that is what is being displayed over here. So that is normalized load impedance is point A. Point A. So once we plot that, what is the next step we do is we draw the constant VSWR circle. And that constant VSWR circle will have center as the center of the Smith chart, and the radius will be equal to OA. That is the load point and the center of the Smith chart. When I measure this distance, this will be the radius of this VSWR circle what we are representing. So first thing is mark the load point, then using O as the center and the radius equal to OA, draw the VSWR circle. What's the next thing you have to do is, next thing you have to mark a point opposite to A. That is what you have to look out for. So now here we have marked the input normalized load impedance value. Now we need to identify a point B which is actually opposite to this point A, which is relevant to the load impedance. So what we do is we join point A and point O and extend it towards point B such that the VSWR circle is intersected by this extended line of OA. So you join OA and extend it towards the outermost circle. So in this case, what happens is I will be having a point B which is intersecting the VSWR circle. So this point is nothing but the admittance point which is opposite to that of point A. So this is marking the admittance with respect to the load impedance what we have. First, we mark the point A, which is the load impedance. Then we draw the VSWR circle. Then we joined the points O and A and extended it such that the VSWR circle is intersected by that extended line. So that is marked as point B. So this is the admittance which is present. Now what we need to do is we need to identify few of the parameters like what is the distance associated with the stub and what is the length of the stub. So now what we have to do is, in order to identify the location of the stub, in order to identify the location of the stub, what we have to look out is, so if you look at this chart, sorry. So I have this case. So if I know this point, I have to move towards the load. If I know this point, I have to move towards the generator. So that is what we have to look out when we are dealing with this aspect. Now, what we are doing is we are moving towards the generator. We are moving towards the generator. Therefore, we have to move in the clockwise direction. And up to what point we have to move? So if you just observe this, we marked the point A, we draw the VSWR circle, we joined OA and extended it, we obtained this point. So which is actually the admittance associated, which is opposite to point A. So now here what we are doing is we have G is equal to one circle, which is presented over here. So we have G is equal to 1. What we have to do is, in order to identify the distance at which the stub is to be placed. So from this point B, you have to move towards the generator, that is in the clockwise direction, such that this VSWR circle intersects the G equal to 1 circle. It intersects the G equal to 1 circle. Or else in other way, what you do is you try to identify where is the point which is interaction of G is equal to 1 and this VSWR circle. So you identify that point and you measure the distance between these 2 points. You measure the distance between these 2 points. So this value will give you the distance between the load and the, it will give you the distance between the load and the stub. Load and the stub. So that is what we are doing over here. You marked point A, you draw the VSWR circle, then you obtain point B, which is opposite to A. So therefore, in this case, if you just see this is capacitive, the stub should have a value of inductive. So now I'll not confuse with respect to that. Mark point A, draw the VSWR circle, then mark a point opposite to A, which is point B, and identify a point which gives you the intersection of G is equal to 0, G is equal to 0, and the VSWR circle. So in this case, it is point C. It is point C. So now what you do is you measure the distance between point B and point C, which gives you the distance at which the stub has to be located. It gives you the normalized value. So this is the first thing what you have to look out for. Okay. So that is what is specified over here. That is at what location the stub has to be placed. So for that, you have to complete all those steps. And when you measure the distance, right, you will be getting the distance which is corresponding to the distance at which the stub has to be placed. So now I got to know what is the distance, but what should be the length of that stub? So now what happens is at this point, what we have obtained. So we'll be having a corresponding susceptance value. We'll be having a corresponding susceptance value. So you read that susceptance value over here. You read that susceptance value. Now what you need to do is you need to mark a point which is exactly opposite to that susceptance. Opposite in the sense it negates this susceptance value. It negates this susceptance value. So for that, what we have to do is, so here we have the susceptance value of point C represents the susceptance of the line at the stub connection. So where we are connecting that stub, right, at that point, I have a susceptance which is equal to this value. I have to negate that value. I have to negate that value. That is the thing what I have to do here. So in this case, what I am having is I am having a susceptance of plus JB. I am having a susceptance of plus JB. Now what I should look forward is we have the value of plus JB, that is the susceptance, which is positive in this case. This value of capacitive susceptance has to be neutralized by an inductive susceptance. So if I have to neutralize this, I have to identify a minus JB value. So what I do is, in order to identify this, first and foremost, what I have to look out is, first I have to identify which is minus JB susceptance parameter. We have to identify that over G is equal to zero circle. Over G is equal to zero circle. So G is equal to zero circle is which? It is this parameter. It is this. G is equal to 0 on this, right? So whatever value I have got, so I have got say plus JB over here. I should mark that minus JB value over here. So that is what I try to identify. So that is the point D what is specified. This is the point D what they have specified. Now in order to identify the length, right, what we do is we consider the short circuit point and move towards the point D what we have identified. We move towards the point what we have identified. So it is we move in the clockwise direction. So when we move in the clockwise direction, what we are having is we will be having the length parameter. So this value will give me the length which is associated with the stub what we are discussing. So this is the case what we have to look out, or these are the steps what we have to check out when we are dealing with the Smith chart in order to identify the length and the distance at which the stubs are placed. So let us look at one of the examples and then wind up this session. So we have load impedance ZL, which is 60 minus J80 ohm, and is required to be matched to a 50 ohm coaxial line by using a short circuited stub of length L located at a distance D from the load. The wavelength of operation is 1 meter. Use Smith chart, find D and L. So this is what you have to look. This is what you have to look out when you are dealing with this aspect. So first and foremost, what is the thing they have given? They have given what is the load impedance. They have given the characteristic impedance to which you have to match, which is around 50 ohm. So first step, normalize this load impedance value. So that is by dividing this ZL by Z0. So you'll be getting ZL is equal to 1.2 minus J 1.6. So now since this is minus, right, this is capacitive in nature and it is in the lower half part of the Smith chart. So here that is, it is this point what they have marked. So this is the normalized impedance, normalized load impedance what they have marked. So this normalized load impedance, in the next step, what you have to do is you consider center as O and radius equal to OA. Draw a VSWR circle. Draw the VSWR circle. You need to draw the VSWR circle. So you draw the VSWR circle, and now what is the next thing you have to do is you have to mark the point which is opposite to A. So in order to do that, join A and O and extend it such that it intersects the VSWR circle. So now you will get point B. So what is the next step you have to look out? Once you have marked this point B, you have to identify the point where VSWR circle and G is equal to 1 circle intersect with each other. So that is point C, which is specified over here. So next what we have to do is we measure what is the distance between these 2 points, that is B and C. So in order to measure that, what you can do is you can extend this OB line and intersect it at B dash, and you can join OC and extend it such that it intersects the outermost line at C dash. Now you measure the distance. So this distance based on the estimation, it is around point triple one. It is point triple one. So this gives you the distance. This gives you the location at which the stub has to be placed. So now, what is the next thing you have to do is you read what is the what is the susceptance value over here. So here, if I just check, the susceptance is around something. It's not clear. Okay, so I'll just check it from this part. What is the susceptance? So susceptance is around 1.5. Susceptance is around 1.5. So here, this point is having a susceptance of 1.5. Now, next, we have to mark opposite susceptance value. So here it is 1.5, right? We have to identify where is 1 point minus 1.5. We have to plot this, but we have to consider what? We have to consider G is equal to 0 circle. G is equal to 0 circle. And we have to identify that susceptance value. So which is actually equal to point D over here. So now what we do is, since it is a short circuited stub, in order to measure the length of that stub, we start from this point B, which is the short circuit point, and move towards the point D. So when we move towards the point D and when we measure that value, it is around 0.094, which is the normalized length what we are specifying. So this gives you the normalized length of the stub. So the overall length of the stub will be equal to 0.094 times lambda. So this is the problem which is associated with identifying the length and the distance at which the stub has to be placed. So this is all what we have for this session. Now we will be meeting in the next session. Wherein we'll be having some discussions associated with the aspects what we have discussed till now. So let us meet in the next session. Thank you.